A basic shape is a square. It has 4 sides and 4 corners. Then, if we add squares connecting to the original square, we can get shapes like this. But these corners are no longer corners. They are now vertices, and these sides are no longer sides. They are now edges. We took this idea, and instead of using arbitrary shapes like this, we looked at a map of the United States.
We were able to create a map using state borders as edges. First, we wondered how many colors it would take to color the edges without allowing a single vertex or state to have more than one edge of the same color adjacent or connecting to it. First, we wondered how many colors it would take to color the edges without allowing a single vertex or state to have more than one edge of the same color adjacent or connecting to it. The resulting graph looks something like this. Tennessee was the state with the most colors. We hypothesized that whichever state had the most borders resulted in the minimum number of colors required for the map. South America needed 10 colors, and Brazil had 10 borders, which was the greatest number of borders for any country on the continent. In Africa, we needed 9 colors, and the Democratic Republic of the Congo had the greatest number of borders with 9. This led to the conclusion that whichever state had the most borders dictates the number of colors. We called this theory the Tennessee Theorem. The number of borders for a particular state would be called the order of the vertex in graph theory. By this, the number of colors necessary depended on the vertex with the highest order. However, this got us thinking. What if we wanted to travel throughout the states? Could we find a short path between 2 destinations? What if we wanted to hit every state border, thus every edge, without any repetitions? Would we be able to do this with the world map? Using the Tennessee Theorem, we came to the conclusion that there must be some central hub in the world that makes paths shorter. By paths, we mean the number of edges separating 2 vertices in the graph. We are looking at countries as if it is very easy to pass through the entire country, no matter how large the country is, or whether the country's land is separated. We realized that Russia, for the majority of the world, and Brazil, if you started or ended in South America, were the 2 major hubs on the world map. Moreover, there were some sections of the world that immediately increased the length of a journey, such as Central America. There is really only one path straight through Central America, connecting the 2 American continents. This path really lengthens the path between 2 countries because there is no shorter way around it. Through trying to create these paths by hand and guessing and checking paths, we experienced a lot of challenges. It seemed like every time we went back to look at what we'd done, we'd find a mistake in our borders or in a path that we'd never tested before. This was really frustrating, so we tried to find a more efficient way of creating our graphs and testing path links.
So our solution to this problem happened upon us by pure luck. One day, while Kathryn was in the computer lab doing our daily checking of our borders to make sure everything's all right, Dr. Stonedahl happened to walk past her, and noticing all the bright colored lines on her screen connecting the entire world, he was intrigued and inquired about what was going on there. And she informed him that it was the project and everything that we were doing and what was going on. And being the fantastic, amazing computer scientist that he is, he thought surely there was a better way to do it with computers, and to which he was right. Him and Kathryn went through and they created this Python code. And what the code does is it goes to an HTML, and we gave it a Wikipedia HTML, and it parses information from it, and what it's grabbing is this. So this is the Wikipedia page. It's got countries and everything listed, and so what it's looking for is these words in italics, because only our countries are in italics. So it finds something in italics, reads that, grabs the dash mark, and then reads the next thing that is in italics. So reads the first italics, it knows, hey, that's a country, and then makes sure there's a dash next to it, and then reads the next italics, and it knows that those are 2 countries with borders. So this is a gigantic list with a lot of borders, as you can see. Pretty much never get through all of those by hand. So there was a lot. And there was a few we missed, obviously, because we don't know some of the countries. So this was a fantastic way to be able to accurately map all of the borders that we needed. So when the code runs in Python, this is the map that we get out. And while it may look different, these are going to be virtually the same. The only difference is instead of us going through and manually checking each and every border with Google Maps and Google Earth, which, let's be honest, we're humans, we can make quite a few mistakes. This one's parsing from the HTML, so it's going to be a lot more accurate, and to the best of our knowledge, it's the most accurate that we can possibly get with these borders. So while they're going to look different and it's structured different, we got the different colors, it's going to be the most accurate representation of what we have. Now I'm going to throw it over to Kathryn and let her tell a little more about what's going on with this map in specific.
This program plots the world as a graph using strictly land borders. Through this program, we're able to find the shortest pathways between the different countries more easily. We focus more on paths between two countries that travel through the least number of countries, rather than the actual real-life shortest physical distance between the original two countries. Since we used only land borders, it kind of looked like a normal map where the Americas are separated from Europe, Africa, and Asia, which are all connected. However, since France owns a tiny bit of land in South America, this makes all the pathways shorter than we originally realized. The pathway between Lesotho, a country in South Africa, and Chile, or virtually any other country in South America, was around 20 countries away. Now, this pathway is only 14 countries and is one of the longest pathways we can find now. We realized that pathways we found by hand were longer than necessarily needed, which made things much smoother when creating paths and looking for commonalities. For example, because of that land France owns, most paths between the Americas and Africa, Asia, or Europe go through France because the US and Russia border does not exist in this map. But then, we thought about how some countries are connected by water, not a physical piece of land. So we created a list of maritime borders that led us to this graph. This did like neural pathways, but we realized maritime borders and land borders led to connections such as the United States and Russia. Granted, that is more geography than math. So in math, this map looks so different, and we wondered how the different pathways would be with the different countries. The main difference that stood out to us is China now goes from 5 connections to 22 connections. The longest pathway we had found in this map was actually only 10 countries. Also, we had mentioned earlier that Lesotho to Chile was 14 countries. Now it's only 7. We were able to find paths between countries that did not exist before, such as Costa Rica and Panama, because the Panama Canal keeps them separated.